Good morning. Welcome today, where everybody is. So we're going to keep going with chapter 7. Try and get that done today on Monday, so that we don't need to meet on Wednesday. Oh, I just realized too that I need to grade one of the questions on your last test. I didn't realize that until like this morning when I was looking through Moodle and I saw that it said I needed to grade test 2. And I'm thinking, why do I need to grade test 2? There's one short answer. So I will try and get to that ASAP, hopefully sometime today. Okay, and if not today, definitely tomorrow. So sorry about that. So last time we left off how is my connection right now? Are you guys okay? I'm feeling like my connection is a little weak. Can somebody put in the chat if you are okay with my connection? Seems like a hot mess. It's good. Lyric says it's good. Okay. I don't know what's happening on my end here. And my computer is totally freaking out right now. Good. Okay. Well, we're just going to roll with it then. So last time we were talking about balancing chemical equations, or we started to talk about it, this idea of the law of conservation of mass, right? So the amount of atoms that we start with in a chemical reaction need to equal the amount that we end up with. So we need to multiply subscripts, or rather multiply compounds by putting in superscripts. Sorry, I'm so distracted. My screen keeps like buzzing in and out on me. Let me stop share for a sec. Okay. Now it looks good. Try that again. Yeah, something with my share screen. All right, well, we're gonna do the best we can. If you guys have trouble on your end hearing me at some point, or if, I think it might just be my computer's like dying here, let me know. So the only thing we can change, like I said previous, was our coefficients. So in this case, when we put a 2 in the front here, what we're saying is that one methane molecule is combining with 2 of these diatomic oxygens to produce 1 CO2 and 2 of these cute little H2Os. We can go through and actually multiply it out to make sure that they're the same. So carbon, there's 1 on the start, there's 1 on the end. Hydrogens, there's 4 to start with, and now there are 4 to end with. Oxygen as well, there's 4. Why is it 4 on the side? There's 2 of these oxygens, and we take the subscript and we multiply it by the coefficient. So 2 times 2 gives us that 4. And then over here, you want to make sure you add all the oxygens up. So there's a 2 here, so that gives me 2 oxygens here, and then I have an additional 2 oxygens here for a total of 4. That is a balanced equation. We like equations to be balanced. So how do we write a balanced equation, or how do we balance an equation? The first thing you do is write a skeletal equation by writing the correct chemical formulas. So previously here, this would be, going back, this would be an example of a skeletal formula. All right, it's got your reactants in the right place, it has your products in the right place, but you don't have the proper balancing. It's not always given to you like this. Okay, sometimes you get a word problem. Now, I would not expect you to know what methane is because I don't test you on organics, but I could say something like aluminum oxide reacts with oxygen to form whatever, these two products. These are all names that you should know what the formula is. That's from nomenclature. So first thing is to write a skeletal equation with the correct formulas. If you haven't done that, that's all chapter 5 stuff. Next thing, if an element occurs in only one compound on both sides of the equation, balance it first. If there is more than one such element, balance metals before non-metals. So what this is saying is, like in this equation back here, do you see how there's carbon is in one element or one compound here and one compound here? We'd want to start chipping away at that before we went ahead and balanced oxygen. Because here oxygen is split up, it's a total mess. We don't want to deal with balancing oxygen first. We're going to hope to balance the other things, and then oxygen will just sort of work itself out at the end. Third rule, if an element occurs as a free element on either side of the chemical equation, balance it last. So if there's something that's by itself, wait until the end, because if I could put a coefficient in front of that, it doesn't change anything else, right? If I put a coefficient in front of a compound, it changes everything within the compound. So we'd like to save these for last to kind of finish it up. If the balanced equation contains a coefficient fraction, multiply by some sort of whole number to get a balanced equation. And then always go ahead and check to make sure that everything is balanced. Remember, 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 change only coefficients, do not change subscripts. If you change a subscript, it no longer is the formula you started with. So let's do one of these. We've got this here, aluminum. I'm gonna write this over here. So we've got aluminum. Aluminum combines with H2SO4 to produce Al2SO4 3 plus hydrogen gas. Do they put the rest of the phases in? Yeah. So they added the phases here. So this is in solid form. This is aqueous. This is also aqueous gas. So the first thing you want to do is take inventory of everything you have. Now, this one has a polyatomic ion in it, so we're just going to kill two birds with one stone. And I'm just going to tell you that if you have a polyatomic ion and the polyatomic ion doesn't change, so see how it's SO4 here and it's SO4 here? It's like that unit remains constant. One of the oxygens didn't pop off, one of the sulfur and the oxygen didn't separate. If that's the case, you can take inventory of the sulfate as a single unit. So I'm going to write down everything I have. I have aluminum. I have hydrogen. And because the sulfate ion stays true to itself, right? It stays sulfate. I'm going to write SO4 as a little packet. So now I want to take inventory of how much I have of each. So on the starting side, I have one aluminum. So I'm going to put a little 1 here. On the ending side, I have 2 aluminums. I can already see that's not balanced. Hydrogen, I have 2 here and 2 here. And then the sulfate ion, you want to think of it as a unit. There's 1 sulfate ion here. How many do I have here? 3. Okay. So we want to start balancing. We could start, I mean, we can start in a couple different places, but we could start with the aluminum. So there's 2 here. So if I put a 2 here, that will now change this to 2. And aluminum's balanced. Again, I would never want to put a 2 down here. First of all, aluminum's not a diatomic. And second of all, we're changing subscripts. We don't want to do that, okay? So always in front. Next thing, hydrogen is currently balanced. Sulfate's not balanced. So I've got 3 of those sulfates here. So I'm going to put a 3 in front of here. Now that changes sulfate to 3, but what does it do to my hydrogen? 2 times 3 gives me 6. So you may be thinking, oh no, my hydrogen, it was balanced and now it's not balanced. Sometimes that happens, okay? Sometimes we have to unbalance one thing to balance another and rebalance. So if there's 6 there, I need to have 6 on the other side, so I can really simply just put a 3 in front of here, and that will change this to 6. Now I have 2 and 2, 6 and 6, 3 and 3, and this thing is balanced, okay? So what we're telling our audience now is that you actually need 2 aluminums to combine with 3 of these sulfuric acids to produce 1 of these aluminum sulfates and 3 of these hydrogen diatomic molecules. Any questions on that outside of we just need to practice a bunch? How would you know to split it from sulfuric acid, but not the polyatomic ion? In what way, Suzanne?
Like,
Yeah,
you want to keep the polyatomic ion together because it's kind of a package, but wouldn't the sulfuric acid be considered like a package as well, or?
Yeah, I'm just talking about keeping it as a package when we're taking inventory on how many of them we have. So instead of having to go through the laborious process of, and you can do this, of taking S and O, and then you go, okay, I've got 1 S here, and I've got 3 S's here, and I've got 4 O's here, and 12 O's here. You can think of it as a unit, okay? That's what I'm talking about. Just so that, just to make it easier for you when you're figuring out how many you have on each side. If that doesn't feel intuitive, you can always ditch that and you can take inventory of things individually. But then you're going to start to get, you know, multiples, bigger numbers for some of those. Cool. So let's see if the slides have any more good examples for us. All right, so they went through and balanced this thing. Balance polyatomic ions as a unit as long as they stay intact. Excuse me, intact. All right, so we are good. Oh, here they actually separated the sulfur and the oxygen out. I like to treat those as a unit as long as they stay a unit. And that's the only example that they give you for balancing. You all should be perfect balancers now. We shouldn't have to do any more, any more practice on that according to the slides. Let's pull up a worksheet here. Okay, so there's a bunch of practice here. So first one, I'll do a couple of these together, and then I'm gonna have you do a couple on your own. Zoom in here a little bit. All right, first one here, I've got nitrogen gas combines with hydrogen gas to produce this thing, NH3, which is called ammonia. And I'm gonna write on you, and you're not gonna let me just annotate. All right. So first thing we wanna do is take inventory. I'm gonna have to do it over here. I've got nitrogen and I've got hydrogen. So on my reactant side, I have 2 nitrogens and I have 2 hydrogens. On my product side, I have 1 nitrogen and I have 3 hydrogens. So I guess I can start off, if there's 2 nitrogens here, I need to have 2 nitrogens here. So I'm gonna put a 2 in front. I'm gonna double up how many of those I have. That changes this to 2. We'll then change this to 6, which I actually like. The 3 was kind of a problem because this is a diatomic and those diatomics are always gonna be multiples of 2. So now I can easily put a 3 in front of here, and that's gonna change this guy to 6, and we are the same. This has an inferred 1 in front of it. You can write the 1 in if you want. You don't have to though. I mean, if I'm writing if the compound's there, I have to have at least one of them. Otherwise, why am I writing the compound? All right, let's look at the next one. So we've got KClO3 breaks up into KCl and O2. This thing here, this ClO3, is a polyatomic ion. But do you see how it's a unit here, and then over here it's like split seed up? I would just take inventory of everything separately in that instance. So I've got K, I've got Cl, and then O, 1 K, 1 Cl, and 3 Os to start with. On the inside, I have 1 K, 1 Cl, and I have 2 oxygens. Okay, so this scenario here where you have odd even number. You could be like, well, my Ks are balanced and my Cls are balanced, so I just need to fiddle around with O. What can I put in front of this to make it a 3? Nothing. So I'm actually going to get my oxygen on the odd side to an even number. And the fastest way to do that is to throw a 2 in front of it. If I put a 2 in front of it, it changes this thing to 6. I like that. It also throws these off. That's okay. 2 and 2. We can go back and balance our oxygen. So 6 over here, I'm going to put 3. That changes this to 6. And then I'm just going to finish it off with a 2 right there. And that goes 2 and 2. Any questions on that outside of, we're just going to practice some. You guys are just so ready to practice. You're like, oh my gosh, I just love balancing equations at 8:20 in the morning before coffee. Please, let's do it. Okay. Then I want you to work on problem, let me circle, 3, 4, 5, 6, 7, 8. Okay. Let's do those. And then 9 down at the bottom there, I'll leave that one. We can do that one together because that one's a little tricky. So I'll give you all, it's 8:20. I'll give you just close to 10 minutes to do those. Obviously, while you're working on them, if you have a question, please throw it in the comments or just unmute yourself and you can ask me what the deal is. Okay, let's mess around with these. So this guy here. All right. Now, as you get better at these, and it may start to feel a little bit more intuitive, you might not have to take inventory like every single time, writing everything out. Um, but only if you're like super, super confident with your skills. Otherwise, it doesn't take that long to write out what elements you have and how much you have. So I've got 1, 1, 2, 1, 2, 1. Okay, kind of like that when there's like a 2 on one side and a 2 on the other. So sodium's good. I don't know, let's go at chlorine. Okay, so there's 2 on this side. So I'm gonna put a 2 here. Changes this to 2, and it's like, oh no, what happened to my sodium? That's all right, because I can balance it on the other side by throwing a 2 here. That balances sodium, and then it also takes care of the fluorine. So we're done. So 2 2s for our coefficients there. Next guy, we've got, the formation of water. Okay, so I've got hydrogen, oxygen, 2, 2, hydrogens, 2, oxygens, 1. Okay, this is one of those situations where well, no, I can just put a 2 here. I don't have to do anything with that. So that gives us the 2, that changes this to 4, and then I put a 2 here, and that balances this to 4. Okay, so tell me if I'm going too fast, too. If there's one that you got really stuck on, these ones are relatively simple. Okay, what do we got going on here? This is one where I'm gonna take inventory separately. Do you see how it's hydroxide over here? And then over here, oxygens and hydrogens have changed positions. Yeah, we're gonna just, it's meth, and there's a hydrogen over here. We're gonna take those separately. So I've got lead, oxygen, hydrogen, and chlorine. I start with 1 lead, I end with 1 lead. I start with 2 oxygens. I end with 1 oxygen. Hydrogen, I have 2 oxygens here, or 2 hydrogens here, plus another hydrogen. I have 3 hydrogens, okay? Over here, I've got 2 hydrogens, and then chlorine, 1 chlorine, and 2 chlorines. So let's see, hydrogen is split up here. Blech. We're gonna just leave that to the end and hope that it works itself out. Lead's already balanced, oxygen is kind of messy. This is always gonna be a multiplier of 2. So I'm probably gonna have to put a 2 here to at least get this to a 2. So that's gonna change my hydrogen to 4, changes this to 2. Then I could do, I don't know, let's do chlorine. Okay, so there's 2 chlorines here. So I can do 2 chlorines here. Also changes hydrogen to 4. Ooh, we made it happen. 2 and 2. A lot of 2 and 2s. Now we've got, this one does have a polyatomic ion that stays intact, sulfate and sulfate. So I'm gonna go aluminum, bromine, potassium, and sulfate. I start with 1 aluminum, I end with 2 aluminums currently. I start with 3 bromines, I end with 1 bromine. I start with 2 potassiums, I end with 1 potassium. I start with 1 sulfate, I end with 3 sulfates. I like when I have these 2s and 3s because it means that at some point I'm gonna have like 6 and 6. We can start with the aluminum. So there's 2 aluminums here. So I'm gonna put a 2 here. That changes my aluminum. It's also gonna change my bromine to 6. So then we can play around with bromine. We put a 6 in front of here. That changes bromine to 6. It also changes my potassium to 6 on my product side. So then let's balance potassium. If I put a 3 here, that changes this to 6 because it's 3 times the 2. And then the 3 also gets distributed to the sulfate, and we have 3, and we're balanced. We're done. Okay, let's go to the next one. These next, this next little set of equations here, or chemical equations, are combustion reactions, and you'll be able to identify those a little bit later. But it's anytime you have some sort of hydrocarbon being carbon and hydrogen, combines with oxygen, right? You see how they're different hydrocarbons, but they're all doing the same thing. They combine with oxygen to produce CO2 and H2O. This is a combustion reaction. So this first one here is the combustion of methane. So I've got carbons, hydrogens, oxygens, 1, 4, 2, 1, 2, 3. Okay, balance the carbons first. When you're doing combustions, balance the carbon, balance the hydrogen, then do the oxygen. Carbon's good. Hydrogen, I've got 4 here and 2 here. So I'm going to put a 2 here. That'll change this to 4. Ooh, and then that changes my oxygen to 4 as well. I like that because now this is an even number and I can just throw a 2 in front of there to get to 4. Done. Next one, same things, just different quantities. So we've got carbon, hydrogen, and oxygen, but this time I have 3 carbons, 8 hydrogens, and 2 oxygens, 1 carbon, 2 hydrogens, and 3 oxygens. So balance your carbon first. Put a 3 here. 3. Balance my hydrogen. So there's 8 over here. So I gotta put a 4 here. That will change this to 8. It also changes my oxygens. So what do I've got going on? I've got 6 here, right? 2 oxygens times 3 is 6 plus 4 gives me a total of 10. Now I can finish that off by putting a 5 over here, and that will give me 10. We are balanced. Now this next one is a little sticky. So we've got, I'm going to write it on a different, on my board. We have octane, yeah. So we've got, or no, not octane. We've got, yeah, no, octane, yeah. Okay, so plus oxygen produces CO2 and 8, where am I? H2O. Okay, so we've got our carbon, our hydrogen, and our oxygen. 8 carbons, 18 hydrogens, 2 oxygens, 1 carbon, 2 hydrogens, 3 oxygens. So first we balance our carbons. So if I put an 8 here, that'll change this to 8. It changes the oxygens as well. I'll come back to that in a minute. Hydrogen, I've got 18 over here, and I've only got 2 over here. So I'm going to put a 9 there. That changes this to 18. Now we've got to add up how many oxygens we have. So in this case, I've got 9. 8 times 2 is 16, plus the 9 equals, I'm like spacing out here, 25? 25, yeah, I can add, I swear. So I need 25 over here, but it's times 2, right? So what could I put here? Well, I could put a 25 divided by 2. Just bear with me here. Okay, why am I going to put it over 2? Because the 2 and this 2 will cancel out and you're left with 25 oxygens. All right, so now I've got the same number of oxygens. Why don't I quite like this? Because it's a half number. So the quickest way to do that or get rid of that is to multiply every coefficient by 2 to get rid of it here. So I'm going to throw a 2 here. That will change this to just simply 25. 8 will now become 16, and 9 will become 18. So we've got 16 and 18. That throws all these numbers off. This becomes 16. This is also 16. Hydrogens, oh boy, 36. 36 over here, and then 25 and 25 for those. No, not 25, 50. 50, because we multiply by 2. Okay, that one's a little icky. That's probably like the ickiest of the ones you'd see, except for the word problems, which we're going to do next. So any questions on this like balancing technique? All right, so what if you aren't given this like awesome little nifty skeletal formula? Instead, you're given word problem. Well, you don't have this. You get this. Sodium combines with chlorine to produce sodium chloride. I want you to write a balanced equation for that. So let's try it out. Minimize this. No, come on. As small as you're going to get for me. Okay, so we're going to do this one right here. Sodium combines with chlorine to produce sodium chloride. So I want to write a balanced equation. I need to make sure that I honor each of the compounds that I have. So when I'm working on these, I like to like write on the word problem, and I will underline my reactants. So I've got sodium combines with chlorine. And then I'll circle like the to produce or create or decomposes or whatever to signal, okay, these are my reactants. And then the other side is in fact a product. Combines with, that's going to be like a plus symbol. So now I need to write all of these correct compounds out. So first I write sodium. Ask yourself every time you're dealing with a free element, which is an element that's just by itself, is it a diatomic molecule? So is sodium a diatomic molecule? What's the diatomic molecule? Have no fear of ice cold beer, right? Those non-metals that like to bond with themselves. Sodium is not a diatomic molecule. So I can just write sodium as Na. Combines with chlorine, okay? Chlorine, is it a diatomic molecule? Yes. So you don't want to write chlorine as Cl and leave it like that. It needs to have a little 2. If you don't do that, it'll throw all the balancing off. To produce sodium chloride. So sodium chloride is sodium mixed with chlorine. Sodium, remember, has a positive charge. Chlorine has a negative charge. Flip-flop, NaCl. Now I can take inventory and balance. So I've got 2 chlorines on this side. So I need to put a 2 here to have 2 chlorines on this side. And then I'm going to throw a 2 in front of the sodium to balance it out. Not too bad for that one. Let's do the next one, which is a little ickier. Okay, so solid copper reacts with aqueous silver nitrate to produce aqueous copper 2 nitrate and silver metal. Oh, fun. So I'm going to underline what I have. I have solid copper and it reacts with aqueous silver nitrate. And that's just telling you what the phase is to produce. So I'm going to circle the produce. Aqueous copper 2 nitrate and silver metal. So I have to start writing all this stuff out. So copper, silver copper, or solid copper rather. So copper's symbol is Cu. Is copper a diatomic molecule? No, none of the metals are diatomic molecules. So I'm just going to leave it as copper with a little s. Combines with aqueous silver nitrate. Ugh. Okay, what was silver nitrate? Silver nitrate, so silver is Ag with a plus symbol. Nitrate is NO3 with a -1. It's a 1-to-1. So AgNO3, and I'm going to put an aqueous symbol because it tells me that it's aqueous. To produce, or the products are, so that's going to be my arrow. Aqueous copper 2 nitrate and silver metal. Okay, so aqueous copper 2 nitrate. So copper 2 nitrate means that I'm dealing with copper with a 2+ charge, nitrate, NO3 with a minus, flip-flop, CuNO3 2. And you may be thinking, oh, but I only have one nitrate over here. How can I have two nitrates here? We will balance that after the fact. The first step in doing these is always to make sure you write a correct formula. Don't worry about how many you have on each side. Plus what is left over. Oh, and it says that this thing is aqueous. Okay, so we'll put a little aqueous symbol there. Silver metal. So silver metal is Ag, and is it a diatomic? No. So now I can balance. So I've got copper 1 and 1, silver 1 and 1, nitrate. I've got 2 here and I've got 1 here. So I'm going to put a 2 there, and then I'm going to put a 2 there. So this requires nomenclature. Blech. Doesn't go away. All right, I want you to do this one here, number 3. And let's do number 6 as well. So solid iron 3 oxide and carbon monoxide produce iron metal and carbon dioxide. And then aluminum reacts with oxygen to produce aluminum oxide. So write its skeletal formula, then balance it. I'll give y'all, about 5 minutes for those. Okay, let's look at these. So, clear this out. All right, we got solid, iron, 3 oxide, and carbon monoxide. So iron 3 oxide looks like this, Fe2O3. Remember that 3 is not talking about how many irons you have. It's talking about what the charge is of the iron, and then you've got to go ahead and come up with the formula. Plus carbon monoxide, that's CO, produces iron metal, Fe, and carbon dioxide gas, CO2. I'm not going to put all the phases in. All right, so I've got iron, oxygen, carbon, 2, 4, 1, 1, 1, 2. Okay, I mean, I guess we can, I don't know. I guess we can go with we've got to balance the oxygen at some point. So I've got to put, let's see, make sure I did these correct. Carbon monoxide. Yeah, we could start with iron, so I could put a 2 there. That changes that to 2, doesn't do a whole bunch. Now we've got to do the rest of it. Okay, so 4 oxygens here, 2 here. So if I put a 2 here, that changes this to 2. It changes this to 4. Now I've got to balance this. So I'm going to put a 2 here, which changes this to 2. Changes this to 5. So I'm going to put a 2 here. That's going to change this to 4. It'll change 6, 7, changes this to 7. I'll go back around. I'm going to put a 4 here. 7. Let's see, 2, 2, 4. Oh, come on, Candace. Where are your balancing skills this morning? 0. Okay, so then I'm going to put, there's not much I can put there. Oh man, what's going on? Make sure I've got this correct. Look at the answer now. Cheat. 2, 6, 4, 6. Yeah, I guess I didn't go around enough. So yeah, if I have a 2 and the 4 here, that gives my that makes my oxygen 7, and I don't like it being an odd number because it has to be a multiplier of 2 over here. So I'm going to change this then to 3. That changes this to 8, which means I can put a 4 here. That changes this. Where are we at? We've got 3 here. Changes this to 4. Oh man, this one's messy. This one's messier than I thought it was. What? 2, 6, 4, and 6. 2, 4, we're good there. Still working around. This we've got 4. Here we've got 3 oxygens. We've got 8. Here we've got 8. These are not matching up, so I'm going to multiply this by 2 to get an even number to give me 6. That changes this to, we've got 6 plus this gives me 12. And then over here, we've got our 4. This I'm going to change to, no, I don't want to do that. I got to start over. I confused myself. I have confused myself. Let's go on, start all over. So we had what, iron 3 oxide, Fe2O3 plus carbon monoxide produces, what do we say, produced iron and CO2. Iron, oxygen, carbon, 2, 4, 1, 1, 1, and 2. Okay, so let's try this again. So our irons are off, but I know it's not really going to do a whole bunch to put a 2 there. Oxygen, 3, 4. Okay, we've got 2 here. So I can put a 2 there. It's going to change this to 4, changes this to 2. So I could put a 2 here, which changes this to 2, but changes this then to 5. So I'm going to put a 2 here to get this to an even number, which will change this to 4. We've got 6, 7, 8. That means I need to change this over here to a 4. Now we have 4 here. And we got to play around with these oxygens. I don't really want to change these two because they're sort of locked in place. There's 4 there and there's 4 there. So I'm going to just mess around with these two so that I can get to a place where my oxygens are balanced. So we can start by bumping this up to a 3, which would change this to 3, change oxygen to 3, 5. I don't really want, well, let's go with a 4 because I always want this number to be an even number of oxygens because this is multiplier of 2. So if we put a 4 here, change this to 4, that's 4 plus the 6, that's 10. Put a 4 here. Four here, that's going to change this to 4. Oxygen is now 8. Okay, we're not there yet. We're getting closer. So we could change this to 6. It's going to be 6. That changes this to 6 plus the 6 is 12. I put a 6 here. That will change this to 6. And then this will also be 12. So then we're balanced. 2, 6, 4, 6. Shouldn't that just be 1, 3, 2, 1? Yeah, 2, 6, 4, 6. So we could narrow it down to 1, 3, 2, and 1 after the fact. I think I might have done more work than I needed to on that one. So if you ever have it where they're all divisible by the same number, you divide them down. Okay, so it's 2, 6, 4, 6. And if you're like, I got 1, 3, 2, and 1 pretty easily, then you go with that. All right. Well, that one was not working for me this morning. My juju wasn't there. Let's do another one. Maybe I can redeem myself here as an instructor with aluminum and oxygen. I better be able to with this one. So we've got aluminum and oxygen produce aluminum oxide. I'm going to do this in a sort of haphazard student way. I'm going to do it in red because it's wrong. So this is what I tend to see students do. They're like, aluminum combines with oxygen and produces aluminum oxide. They're like, okay, aluminum. with oxygen. And it gives me aluminum oxide. I'm done. And look at that, it's balanced. Oh my gosh, ding, ding, ding. Okay, that is so wrong for so many different reasons. Aluminum, the only thing that's correct in this is the aluminum. They got that right. So aluminum is by itself. It is an elemental material. It doesn't have that diatomic quality, but oxygen has a diatomic component. So I need to put a 2 there. The other thing is the aluminum oxide. This is so not aluminum oxide. Aluminum oxide is Al with a 3 plus, O with a 2 minus. I need to flip flop. I get Al2O3. Now I can go ahead and balance aluminum, oxygen, 1, 2, 2, 3. This is an odd even mixture. So I'm going to put a 2 here to get this to an even number. Then I can throw a 3 here to get it to a 6. And then what that would change to a 4, sorry. And then just put a 4 there. This is what it should look like. Okay. This is bad. Questions on that, on going from word problems to skeletal to balanced equation? Now, is every single one going to be on the exam going to be given to you as a word problem? No, of course not. Maybe 1 or 2. So if this is just like horrible for you, you could probably put it aside and spend your time studying other things and still be okay. But there will be 1 or 2 where it requires you to do that. Okay. So aqueous materials, aqueous solutions. So what is that? What does that aqueous thing mean? Well, when a compound is soluble, you'll hear me say the word soluble a lot when talking about aqueous things. A soluble compound, it means it dissolves in that solution. So salt is soluble in water. A compound is insoluble if it does not dissolve in that liquid. So like silver chloride, for instance, is not soluble in water. So we wouldn't say that it's aqueous. An aqueous solution is a homogeneous mixture of a substance that is happening specifically in water. So I can't say aqueous solution for something dissolved in like hexane or oil. I have to say it has to reference only water, hence the aqua or aqueous. Know that when an ionic compound, so ionic being a metal and a non-metal, dissolves in water, they will dissociate into their component ions. So sodium chloride, if it's being presented as a solid, these two things are combined in that 3-dimensional lattice structure. But when I'm presenting sodium chloride as an aqueous solution, it's really little sodium plus ions and little chlorine minus ions floating around in solution. So you can kind of think of these two as like partners, but are like they're dating, right? But then they go to this aqueous party and there's a lot of water involved and they get a little loosey-goosey and they separate from their partner, okay? So now they're sort of free to bump into other things. Just sort of FYI, ions as conductors of electricity or electrical charge. Here's a light bulb and there's a battery. If I flip the switch and I want to create a current here, I cannot do it in pure water. All right, I can only run an electrical current through a solution that has dissolved ions in it, or what's known as a strong electrolyte solution. A strong electrolyte solution means that the material that you've dissolved in it completely dissociates. So these charges allow me to conduct electricity. So you can't electrocute yourself by dropping a toaster in pure water. You would have to have tap water, right? Something that has some ions in it. Important thing to note, when you have something like silver nitrate, so that's silver with the nitrate polyatomic ion. When this thing gets thrown into water, it is aqueous. it will break apart into its constituent element or its constituent components, but the nitrate itself doesn't break up. All right, so what we have now is a packet of silver. And just like I've sort of told you throughout the semester, kind of treat your polyatomic as a packet, continue to treat it as a packet here. Why? Because the bond between nitrogen and oxygen in this polyatomic ion or this little packet here, that bond is a covalent bond. They're sharing the electrons. This is much stronger than the pull of the water. So we want to keep our little nitrate on its own. Okay, here's an example of something that doesn't dissolve in water. Silver chloride, AgCl. So I throw that thing in water and it remains as a solid, and you would be able to visualize this or see it in real life because there would just be a hunk of material sitting in the liquid. It wouldn't disappear or appear to disappear or dissolve. So how do we know if something is soluble in a given liquid or insoluble? There are these rules. Usually it's like an appendix in the back of your textbook that has all the different solubilities. I don't expect you to have these memorized, but you do need to be able to reference them. Okay, so compounds that are usually soluble. Compounds containing lithium, sodium, potassium. So all the things, those things that are in that first column on your periodic chart tend to be soluble like all the time, okay? Ammonium, nitrate, acetate, these things also tend to be soluble. Now, if you have compounds that contain chlorine, bromine, or iodine, you have to ask yourself a second question. Do these things combine with silver, mercury, or lead? If they happen to be combined with silver, mercury, or lead, that means they are going to be insoluble in solution. So bromine combined with silver is an insoluble solution. It means that it's going to form a precipitate, or it's going to be a hunk of material down at the bottom. If chlorine is not combined, or bromine or iodine is not combined with one of these three, anything else, it will be soluble. All right, so that's how you read these charts. Here's all the solubility charts. Here's compounds that are mostly insoluble. So like hydroxide, that is usually insoluble unless it's combined with lithium, sodium, potassium. If it's combined with these, or ammonium, if it's combined with these, it's going to be soluble. But other than that, you kind of just keep asking yourself questions. You go down the chart from there. All right, here's some more solubility charts, yada, yada, yada. So why do we care about solubility charts? Well, because they are useful for these things called precipitate reactions. So a precipitate reaction, and you'll need to be able to identify these, and you'll need to be able to come up with possible solutions. A precipitate reaction is when two things that are aqueous come together. So we pour two aqueous things together, and then all of a sudden a solid forms, or something insoluble appears. The solid that forms is known as a precipitate. So let's look at this equation here. Up at the top, you would be able to identify that this is a precipitate reaction. Why? Because the first thing is aqueous, the second thing is aqueous. We mix them together, and what happens? Bam, I get a solid. All right, this is what it would appear like if we were to do it experimentally. You'd have a clear liquid mixing with a clear liquid, and then all of a sudden this sort of yellowish precipitate, cloudy precipitate, would start to form and sink to the bottom. So how does that happen? Anytime we do this is no reaction, we'll go back to that. How does that happen? So let's look at this thing here. So I've got my potassium iodine, and it's in a container over here. And what we said was when we put it with water, it's aqueous, it gets a little loosey-goosey, it separates from its partner, right? So now they're all their individual ions. Same thing happens with lead nitrate. This thing is also aqueous. It's over here and the partners broke up. All right, so this lead was connected to two nitrates. Now they're all sort of free floating on their own. So what I'm going to do is take this beaker over here, I'm going to pour it into this beaker, or vice versa. Now, like, it's a big party, okay? So That couple over there and that couple over there, they all are in the same space. And what ends up happening is everybody gets to sort of bump into each other and see how the night goes. Well, if potassium and iodine bump into each other, they're already in a fight, so they don't want to make that happen. Lead and nitrate, again, are not really feeling each other tonight, so they're going to stay away from each other because that combination just creates something that's aqueous again or dissolves. But they're metals and non-metals, they can sort of flip-flop partners. So this metal here, the potassium here, can try out nitrate. All right, so potassium is going to bump into nitrate and we'll get potassium nitrate. Now, if I go to the solubility charts, potassium nitrate is in fact aqueous. So those guys didn't really make it happen. But that like magic combination, here's lead and here's iodine. And they see each other from across the room, right? They're looking at each other and they come together and wham, they form this solid. Okay, so like magic has happened here. And so what we will find is that when they flip-flop partners, we get this solid forming. Oh my gosh. So sometimes, because we're all adults here, sometimes you can think of it as like a swingers party, and this is just like where the magic happened. But this is a conservative swingers party. So metals do not combine with metals, okay? And non-metals don't combine with non-metals. They only metal to non-metal. So we're never gonna take my metal potassium and put it with my metal lead, all right? It's always gonna be outer guys and then inner guys. So just make sure that's how you're flip-flopping your partners. How do you know which one's the precipitate, or if a precipitate even forms? You have to be able to reference the solubility charts. So go back here. What happened here? This says no reaction. If I have potassium iodine and I mix it with sodium chloride, nothing happens. Why? Because the possible other option for these is what? I'm going to take my potassium and I'm going to mix it with my chlorine, and I'm going to take my sodium and mix it with my iodine. Those are all aqueous. So in this situation, there's no precipitate. Everybody just stays in an aqueous solution. So we would classify that as no reaction. So I want you to try to come up with the possible products, and notice that the products have to be charge balanced, okay? So I want you to come up with possible products for this here. It sort of already gives you the arrows, but try it out. So we've got sodium carbonate and copper chloride. I want you to write the two possible products, and I want you to make them charge balanced. Oh my gosh, it's 9:14. No, we're not even going to do this. Okay, we're just going to stop now. We'll do this when we come back next week. All right, so if you have any questions, stay around. Otherwise, enjoy this like super rainy, cruddy day. It's a good day to take a nap, I think. I'm already ready for a nap, and it's 9:16. So let me know if you need anything. Otherwise, I will see you all next week. Do your labs, do your homework, yada, yada. Okay, bye.